All right, so today's lecture is going to finish up Module 3. We're going to talk about electron energy and momentum, which is short for E, abbreviated by E and K. So just to give context here, last time in class what we did is we've been talking about mobility in the context of energy bands and carriers. So in this chapter so far, we've talked about what is doping, okay? There's N-type and P-type dopants. We looked at what the energy band diagrams look like when you dope a semiconductor. Then we started looking at mechanisms of how they move. We talked about drift current and how these carriers can move in the response to a voltage, and as they move, they bump into things, and those collisions, referred to as scattering, they slow down the electron. And because of that, there's something called electrical resistance that develops. We connected the concepts of scattering with electrical resistance. There's one more piece of the puzzle here that helps us understand energy band diagrams to a further degree. We won't be spending too much time on energy and momentum in this class, but it's important to understand it in the context of direct bandgap and indirect bandgap semiconductors. Okay, and if you end up taking a more advanced class on solid-state electronics, this type of thing turns out to be very important. So, what we're going to find out is that the energy band diagrams are actually more complicated than just position versus energy. So, in the last module, we learned that electrons, actually this module, we learned that electrons in the crystal can exist in certain energy states with energy E, and that that state describes the energy of the electron. So in the last module, we talked about isolated atoms, and we said there's discrete energy states, right? And what happens to those discrete energy states when you bring the atoms closer together?
They become bands.
They become bands, right? So they call them band formation or band splitting. And it causes the energy bands to split up with very small amounts of energy between them, very small gaps in energy. So electrons can move about those energy bands because there's all these energy states at energy levels very, very close together. So it's easy for the electron to jump from one energy state to the next. By contrast, when you have a region of bandgap, it takes, if an electron wants to go to the next highest energy state, it's way, way high up there. So the electron can't easily do that. You have to supply a lot of energy into the system. So that's what we're talking about when we're talking about the energy state. In isolated atoms, there's discrete energy states. In crystals, there are many energy states that are arranged in energy bands. All right? So that's what E is. That's the energy of the electron. Now, to describe moving electrons. So now we're talking about putting an electric field on the semiconductor, so the electrons start to move. And so they're jumping from state to state as it moves from left to right or right to left, whichever direction the voltage is. And so as these electrons are moving, we have to consider that they have momentum. So a moving electron travels like a wave. You can think about it traveling as a particle. You can also think about it traveling as a wave. Thinking about electrons traveling as particles, as we did in class last time, the electrons are moving, they're colliding, they're bouncing off, and they're going back in that direction. They get pulled back in that direction by the electric field. That's an electron moving like a particle. When we think about an electron moving as a wave, the way that it moves through the crystal, it has a wave function. Okay, remember how we talked about a wave function in the last module? The wave functions come out of what? What determines the wave function of an electron? The wave number? The wave number describes the wave function, sure. But what determines it?
Which theory?
Well, we know the Schrodinger equation determines, but what physical thing?
Wavelength, frequency, wavelength.
No, not quite. I don't think I'm talking about the electrostatic boundary condition, the arrangement of atoms in the crystal, right? The arrangement of the atoms in the crystal lead to a potential condition, right? Meaning like there's all these nuclei scattered about in 3D space, right? Some places have high potential, some places have low potential. That's what I'm talking about, a potential field. Okay, that potential field is the boundary condition for the Schrodinger equation, and that boundary condition is used to solve the Schrodinger equation. That gives you the wave function. So the distribution of atoms is very important. And one of the things we learned about from Module 1 is that the distribution of atoms is actually different depending on what crystal direction you go in. That's a key point when we talk about energy and momentum. We'll get to that in a second. So, but just to remind everyone, there's many solutions and each has a wave number k, and this variable k describes the momentum of the electron. Okay? When we think about the electron moving as a particle, P equals mv. The momentum is equal to the mass times the velocity. When we think about an electron moving as a wave, the momentum is now h times k. Planck's constant times the wave number. Okay, so if we start off with the simplest example, that is the free electron. This is an electron moving through space. There's no atoms in the way. All right, so what is the potential? What is the electrostatic potential everywhere? Zero. All right. Potential is generated by nuclei, by charged particles. If you don't have any charged particles in the space, the potential everywhere is zero. Okay, so this is the simplest example. If we solve the Schrodinger equation for an electron in free space, let me just go back there and remind everyone what that actually means. That way this will make a lot more sense. Go back to Module 2. We solved the Schrodinger equation, if you recall, for a very simple example, a 1D potential well. All right, so we had a boundary condition that went into the Schrodinger equation. We said the potential everywhere is zero. All right, so that boundary condition is passed into the Schrodinger equation. And when you solve the Schrodinger equation under those boundary conditions, remember v of x is equal to 0, and you get this equation. You can refer back to the old lecture if you want to go over this more, but you get a solution. And notice here, this is the key point, that k, the wave number, is a function of e. So if we were to plot e versus k, what would we get? If we square this side, we square this side, E is proportional to k squared, right? Where did this come from? Well, it comes from solving solving a differential equation. This differential equation is in a specific form. It's in this form, cosine of k. This is the solution form, and this is the actual form of the equation. And other people have solved this equation before. And what you do is you find that you have this relationship between k and e. All right, and these were the different wave functions. This is not the important part. The actual solution is not the important part. What's important is this relationship between E and K. Okay, E is proportional to K squared. So going back to Module 3 now, when we draw the E versus K diagram, we draw it parabolically. All right, that means that an electron that has a certain momentum has a corresponding energy E. An electron that has zero momentum that means, what is the wave number for zero momentum?
0.
Yeah, it's 0, right? So P is equal to h times k. If the momentum is 0, that means the wave number is 0. So that's referring to the case right here. Wave number is 0, E is 0. This is a non-moving electron with no momentum. So it has a certain wave function here. E is equal to 0, its k is equal to 0. A moving electron has a different wave function, different solution to the Schrodinger equation. It has momentum associated with it. Now, when you have a free electron, there's actually infinite boundary conditions. There's infinite solutions. Remember when we had the potential well? when we had the potential well, the difference is there were only certain types of solutions. They were all sinusoids with an integer multiple of n. Right? So the boundary condition, the fact that you had high potential here and high potential here and no potential in the middle, that's what constrained your wave functions. In the case of a free electron, there's no constraints to the wave function. K could be anything, and E could be anything. All right. So that's why the wave function looks like this. So the key difference is that between this and the standard energy band diagram. In the standard energy band diagram, the x-axis is, someone tell me, what is the x-axis in the standard energy band diagram? Well, what's the y-axis?
Energy bands?
Yeah, the y-axis is energy, and the x-axis is? Position. That's right. It's the position in the semiconductor. Okay, if you're not sure about this stuff, make sure you go back and look at the lecture notes again and make sure you get started on the homework problems. This is a key point there. I'll make that point again here. When we draw energy band diagrams like this, we draw EC, we draw EV. So the y-axis represents E, energy. And the x-axis typically represents position. So when we start to do PN junctions, we're going to create energy band diagrams where this there's the P side of the material and the N side of the material, and they both have different band structures. We'll get to that later, but the point here is that the x-axis in a standard energy band diagram is the position, and in an E versus K diagram, the x-axis is the momentum of the electron. And this is also showing you the possible energy states for an electron. All right, so in a free electron, the energy increases parabolically with momentum. All right, now let's remind ourselves what electron energy and momentum is in an anisotropic crystal. Anisotropic crystal is what a silicon lattice is. Anisotropic means, for the material scientists, you guys know this already, is that the properties can change with direction. You guys did the homework problems in Module 1, and remember you saw that the surface density of atoms, it differs if you're on the 1, 0, 0 plane versus if you're on the 1, 1, 0 plane, right? Similarly, if an electron happens to be traveling in the 1, 0, 0 direction, like where my mouse is going right now, it's traveling along this this side of the crystal, it's going to encounter a nuclei. The periodicity is going to be about A, the lattice constant, right? Because that's the distance between the atoms along this side. But what if we were to go diagonally like this? What's the distance between atoms if we go diagonally?
Square root of A squared.
What was that? Square root of what? I think I heard it.
There's square, there's 2, there's A.
A root 2 over 2. That's the spacing between the corner atom and the center atom, right? I mean, you guys know how to do that from the first module. The actual calculation isn't important. What's important here is that the distance is different. The periodicity of the lattice is different depending on what direction the electron is traveling, right? If the periodicity is different, then the solution to the Schrodinger equation is also going to be different. Again, if we go back to the simple example of a one-dimensional potential well, when we talked about the Schrodinger wave equations, notice that there was a key point here, is that the L is the distance between the 2 points of high potential. Right? Like wherever you have a nucleus, that's a point of infinite negative potential. Right? So this example from the last module showed us is that the distance, the periodicity, is really important in determining the wave functions. because wherever the potential is, wherever the potential goes to infinite, then the probability of an electron there changes. So anyway, getting back to this, is that the periodicity is going to change the wave function of the electron. So in a typical lattice, the distance between atoms are different depending on the direction. Spacing determines the Schrodinger wave function. And so the electrons can have different energy states depending on which direction they happen to be moving in. Okay, so our band diagrams that we've been looking at before, they haven't been showing the impact of what direction the electron is traveling, nor have they been showing the impact of the momentum. Okay, this discussion question here, I'll just let you figure it out on your own. The atomic spacing along the 1, 0, 0 direction versus the 1, 1, 0 vector. We started doing it just now, but I'd like you to figure it out on your own. So let's look at the E versus K. Oh, sorry about that. The E versus K band structure. In typical semiconductor crystals. So again, the x-axis is showing momentum, the y-axis is showing the energy. But there's a point about these graphs that gets a little bit confusing. The first time I saw it, I found this very confusing. So let's zoom in on here for a second. Okay, x-axis shows K along two different crystal directions. That's the confusing part. If you were to just ignore this half of the drawing for a second. Okay. And just look at this half. Okay. Then this sort of makes sense with what you saw earlier. K, the speed of the electron, and remember K is mass times velocity, it's also K times it, K is the wave number, sorry, not momentum, but this is proportional to the momentum because K is proportional to the momentum. So K on the x-axis, and then the energy on the y-axis. Again, your K on the x-axis, energy on the y-axis. So notice that this says 1, 0, 0. This means that you're looking at the E versus K relationship. So this half of the diagram, this is E versus K along 1, 0, 0 in the 1, 0, 0 direction. If the electron is traveling in the 1, 0, 0 vector, then this is the E versus K relationship, and this is determined by the periodicity of nuclei in the 1, 0, 0 direction. All right, so let's look at what this band structure is. We'll get to this in a second. At zero momentum, the electron has zero energy. That's the top of the valence band. Remember, the valence band describes electrons that are covalently bound to the lattice. So an electron that is covalently bound to the lattice is that's not moving. That would be an electron here on the map. An electron that's moving with a fast velocity, that would be out here on the map. The faster, the larger the wave number, the more momentum that the electron has. So this is, notice that the valence band energies go down like this. The top of the valence band, this is EV. So this line here is EV. And this line up here is EC. So all the bands all the allowable energy states are here and there. So what you notice, you don't have to understand why the shape is like this, but you have to understand what that means. Why the shape is like this is it comes out of the solutions of the Schrodinger equation. As the periodicity changes, the location of the valence band and conduction band changes. What you do have to know is that if an electron in this particular diagram, if the electron is at the bottom of the conduction band, okay, remember that the electrons are most likely to be at the bottom of the conduction band. Can anyone tell me why?
Lower energy state.
It has the lower energy states, right. Remember when we talked about the Fermi level, we said electrons, below the Fermi level, there's a high likelihood that the energy states are full. Above the Fermi level, the energy states are empty. High likelihood that they're empty. So the farther you go up, the less likely it is that the energy state is going to be filled. That's why the diagram shows the electrons near the bottom of the conduction band. And this is showing carriers, holes in the valence band, by the way. So if an electron wants to transition from the conduction band to the valence band, in this type of band diagram, the electron has to lose energy, has to go down in energy, and it has to change momentum. Right? It has to go down and then it has to go across like this in order to get into this state. So it's a two-step process. I'll draw this in blue. So the electron will lose some energy here, and then it will lose momentum like this. Okay? So an electron that happens to be in the conduction band in silicon, interestingly, it's most likely to have has to have a high momentum state. The most stable energy that an electron can have is it has to have some momentum associated with it. What does that physically mean? That says that if the electron is not moving, then it's more likely to be in the valence band, at the top of the valence band. If it is moving very fast, then it's more likely to be at in the conduction band. And if you think about it, that kind of makes sense, because an electron can only really move if it's loosely bound to the lattice, right? A conduction band electron is an electron that's loosely bound to the lattice. Okay. Now what I'm going to do is I'm going to discard all these. Discard those annotations. Where did my presentation go? There we go. Yeah. Okay, so we talked about the energy band diagram on this side. Any questions? Any questions here? Okay, if you're not sure about anything, please feel free to ask. When we talk about the band gap, the band gap represents the bottom of the conduction band, the distance from the bottom of the conduction band to the top of the valence band. All right. When we draw our simplified energy band diagrams, E, C, and EV, the distance between them is the band gap, EG. All right. We don't bother drawing this complex relationship between momentum and momentum and energy. We only just draw the bottom, the absolute bottom of the conduction band, meaning like this part here, and then here we draw the top of the valence band. We're not taking into account the momentum. So it's obviously like a simplification. We just have to be aware of what that simplification is. Okay, now that we've done this side of the diagram, we can look at this side of the diagram. If we were to draw the, let's say this is the positive 1, 0, 0 direction, and so this is the characteristics of an electron moving in the positive 1, 0, 0 direction. What if the electron is moving in the negative 1, 0, 0 direction? What would happen? Yeah.
Just be a mirror.
It would just be a mirror image, right? So there's really no point. If we were to draw the negative 1, 0, 0 direction, it would just be a perfectly symmetric graph like this, right? So that doesn't really, engineers often like to present as much information in the most compact way possible. So what they do instead, they try to present more information on this left side of the plot. So this left side of the plot is showing the E versus K diagram in the 1, 1, 1 direction. So that means X equals 1, Y equals 1, and Z equals 1. If we were to look at the diagram, that's when the electron is traveling from this corner of the cube to this corner of the cube. It's going right through, it's bisecting right through the middle of the lattice. That's the 1, 1, 1 direction. So an electron that happens to be traveling in that direction is going to have a different E versus K relationship. You can see that it still drops off, that high energy electrons have, the valence band gets lower, the conduction band gets lower, but the shape is different because the periodicity is different. And that's a key conceptual question. So again, you don't need to know how these band diagrams are derived, but you need to have a little bit of intuition. So that's for silicon. So the key observation with silicon is that the energy band minima occurs when in the 1, 0, 0 direction, when the electrons are traveling in the 1, 0, 0 direction at a certain momentum. That's when the lowest energy in the conduction band occurs. And the highest energy state in the valence band occurs at K equals 0. And again, to hammer it to death, K equals 0 means the electron's not moving. If an electron's in the valence band, it means that the electron is bound to the lattice. So if you think about an electron that's bound to the lattice, it's not moving, right? So that's a stable energy state for the electron. It's not moving and it's bound. Another energy state in silicon happens to be that it's moving in the 1, 0, 0 direction at a certain momentum, and it's loosely bound to the lattice, and so it's in the conduction band. All right, now let's talk about a different type of semiconductor. The silicon is an example of what's called an indirect bandgap semiconductor. Indirect bandgap means the top of the valence band does not line up with the bottom of the conduction band. I have another slide on this, but I'm just defining it for you right now. So with an indirect bandgap semiconductor, in order for an electron to go from the conduction to the valence band, it has to change energies and it has to change momentum. In a direct bandgap semiconductor, like gallium arsenide, this is what the band structure looks like in gallium arsenide. And it's quite interesting. It also shows it in the 1, 0, 0 direction and the 1, 1, 1 direction. It still has a band gap, but what's interesting is that the bottom of the conduction band lines up with the top of the valence band. So in this situation, an electron that transitions from the conduction to the valence band, when it recombines, we're going to talk about recombination today, it can just it can go directly. It only has to change energy. It does not have to change momentum. Okay. Now, why the band structures line up like this has to do with the mathematics of the Schrödinger equation, but the result is very important. The difference between the two is very important. The fact that an electron only has to change energy, it doesn't have to change momentum, means that a recombination event where an electron goes from the valence to the conduction, from the conduction to the valence band, that process can happen very, very quickly. Whereas with silicon, an indirect bandgap semiconductor, it first has to change energy, then it has to change momentum. So it actually has to go through a trap state. We'll talk about that in the next module. It turns out that type of recombination is slower. And this is the difference between direct and indirect bandgap semiconductors. From a utility standpoint, why we care, it turns out that direct bandgap semiconductors are good at emitting light. So if we are trying to create an LED or a laser diode out of a semiconductor, we have to use materials that can emit light when you stimulate the electrons. So let me talk about what that means. We're going to do a specific example of this in the next module where we do quantitative calculations. Let's just understand it from a qualitative standpoint. You take an electron that's in the conduction band, you energize it somehow, you supply some kind of energy to it, the electron goes up into the conduction band. Then when the electron drops back down, when it recombines, it goes back from the conduction to the valence band, it drops down, it gives off it gives off a photon of light. Okay, and the energy of that photon is equal to the h times the frequency of the light that's emitted. So depending on what the band gap of the semiconductor is, these materials can actually give off different colors of light. For example, there's red, green, and blue LEDs. I think they're quite popular. They're all materials. They're direct bandgap semiconductors that just have different wavelengths associated with them. They have different band gaps, and hence when they give off light of different colors. And that's why a semiconductor gives off only a single color of light. Has anyone ever heard of white LEDs? It's just an aside. You might be wondering, like, why? Well, if semiconductors only give off one color of light, why are there white LEDs? Does anyone know how white LEDs work?
RGB.
Yeah, there's actually two kinds. They're cheating. One is the RGB LED. A white LED actually is composed of red, green, and blue, and all the LEDs are firing at the same time. And so, if you have equal ratios of RG and B, I shouldn't say equal ratios, the correct ratio of RG and B, you can create white light. And those RGB LEDs can actually change colors too. I don't know if you've ever seen like the Philips Hue, like those light bulbs that can change color when you tell it to. It's kind of weird in my opinion, but anyway. There's another type of white LED which is actually inside the light bulb, there's just a blue LED. But there's a phosphor coating, a powder coating on the outside that converts the blue light to white light. So that's cheating. There's actually LEDs, direct bandgap semiconductors LEDs, they give off one wavelength. All right. So this is it. When we draw the E versus K diagram for silicon and gallium arsenide, these are the actual diagrams that show the E versus K in different crystal directions. This is just a simplified diagram, which you can choose to ignore, but it's just illustrating the point that an electron in the indirect bandgap semiconductor has to change momentum and change energy, whereas the direct bandgap semiconductor, it only has to change energy. As a result of that, direct bandgap semiconductors, they don't give off heat, they give off light when they recombine. All right. So let's talk about effective mass now. This is the last concept we're going to cover in this module. And the reason effective mass is important is because it determines the conductivity of material. So again, I want to give a context since we're changing gears here. When we derived or looked at the mobility, I'll give you two pieces of where we used effective mass. When we talked about mobility earlier in this chapter, slide 44, we said that mobility is equal to the charge times the mean time between collisions divided by the effective mass of the electron. And I said we'll talk about effective mass later. Our intuition here was that we thought about the electrons like bumping into things. Electron like bumps into a silicon nucleus, bounces off, but then it's accelerated back in the direction opposite the electric field. So the electric field is trying to push the electron in one direction, but the electron keeps on bumping into the nuclei. So whenever you bump into the nuclei, you have a change in momentum, right? And then the electron bounces off, but then the electric field brings it back in the direction it's supposed to go. It's like a wind pushing on something. So, if a wind is pushing on something, does it have an easier time pushing a heavy particle or a light particle? A light one, right? Similarly, when an electron is slamming into the atoms and is changing directions, to get the electron to go move in the correct direction again, a lighter particle will be able to change directions more quickly, right? So a particle with low effective mass travels faster, higher mobility. Exactly. You got it. Good. I know I go over these concepts many times, but this intuition is really, really important. That's why effective mass appears in the denominator of the mobility equation. Going back even further, when we started talking about density of states, let's see here. There we go. When we started talking about density of states, I also mentioned, hey, there's this mn star here, mp star here. That is also an effective mass that's used to calculate the density of states. Okay, so just for clarification for the beginning, there's two pieces of effective mass that we use. One is for calculating density of states, and one is related to the mobility of the particle. All right, but I spent more time on the mobility part because I think that's a more intuitive understanding of what effective mass is. Now, let's define it more clearly now. So when we've talked a lot about particle and wave duality. So electrons behave as a particle and they behave as a wave. So in the particle-like behavior, the mass is a fundamental property of the particle. Newton's laws from your physics, F equals ma, P equals mv. This P should be a lowercase p, by the way. Lowercase p stands for momentum. And the kinetic energy of a particle is mv squared over 2. So mass, mass, mass. So the mass appears everywhere. In the wave-like behavior, we say that an electron is behaving like a wave, so it moves according to the sinusoidal function. This is a function of x and this is a function of t. This is an equation for a traveling wave. The wave number for this wave is k is equal to 2 pi over lambda. So waves that have small wavelength have a high wave number. And the de Broglie relationship talked about momentum is equal to mv is equal to h times k, the momentum. All right. And so from the de Broglie equation, when we look at the kinetic energy of a wave, we define the kinetic energy as p squared over 2m, just like Newton's laws. Newton's laws is E equals mv squared over 2. Also, it's p squared over 2m. These two are equivalent. So for a wave, de Broglie defined the momentum of a wave, and then we can use this equation for the momentum, E equals p squared over 2m. So this is the top is the momentum of the wave, and the bottom is the effective mass of the wave. So when engineers talk about effective this, effective that, it's like a mathematical jargon. You can think about it as a mathematical jargon. We're trying to relate this particle-like behavior to a wave-like behavior, and we see an m appear in both of these equations. All right? This is the mass of the particle when it has particle-like behavior, and this is the effective mass of an electron behaving as a wave. Okay? So the wave-like model is a better one to use in quantum systems where the electron's moving through closely spaced nuclei. So this definition of kinetic energy becomes pretty important. And because there's an m in there, and we define this m as an effective mass. So the effective mass, it turns out the effective mass of a particle depends on what medium it travels through. So the effective mass of an electron that's traveling through space, in free space, with no nuclei getting in its way, nothing to collide into, is going to have a certain effective mass. In fact, the effective mass will just be the actual mass of an electron, just like 9.1 times 10 to the negative 31. But if the electron is moving through a lattice, then the effective mass changes, because it takes into account the influences of the lattice, which influences the wave-like behavior of the electron. So let's just compare this again. We think about effective mass in a free space versus a crystal. So a free electron is traveling through space, can be described by Newton's laws. Force equals ma, and then force is equal to E times Q. So if you take an electric field and you apply to the electron, the force is equal to E times the charge on the electron. The charge is 1.6 times 10 to the negative 19. And whatever force you apply is going to cause the electron to accelerate at a rate given by Newton's law. So the electric field generates the force, and the force is equal to m times a, so that the force then determines the acceleration. So the force applied to the electron here is the external force. We call that, the voltage that's applied to the system, that's the external force. Okay, and the electron energy is equal to p squared over 2 times m0. The effective mass of the electron in this case is the actual mass of the electron. All right, now for an electron that's confined in a lattice, so let's say you have an electron that's in the conduction band, it's loosely bound to the lattice so it can move around. It's not that it's completely stuck. It can move around, but it's influenced, it scatters, it bumps, it's impacted by the lattice. So the effective mass of the electron, in this case, you still have this equation that holds, E equals p squared over 2mn, but this is kind of like a modified equation, if you will. I'll get to that in a second. So the difference in this case is that the electrons, in the free electron case, you just have the external voltage that's being applied that's acting on the electron, and that's what's causing the electron to move. In the lattice, you have an external force plus an internal force. So let's say the voltage is making the electron move this way, but there's a nucleus here, and that's exerting a positive potential, and that might cause an attractive force. If there's another electron nearby, that might cause a repulsive force. So those are additional forces. So this INT stands for the extra internal force that the electron is subject to as it's moving through the lattice. So what it turns out that it's a great simplification that engineers can do is that it turns out that the electron actually behaves in a similar manner as the free electron, meaning you can think about it in terms of this particle-like behavior, F equals ma and so forth, and it has a certain energy, p squared over 2mo. It actually behaves similarly to the electron if you modify the you modify the denominator from an m0 to an effective mass mn. If you do that, then you can continue using those relationships. So that's why they call it an effective mass. So on the numerator here, you have a crystal momentum. This is just p squared in the free electron. So that's the actual momentum of the electron. Here is the crystal momentum. So the crystal momentum is the momentum of the electrons in the lattice. That's what this graph shows. K is the crystal momentum. I'm sorry, K is related to the crystal momentum. It's not exactly equal to it. Anyway, so crystal momentum over the effective mass. Okay? So how do you actually find the effective mass given an E versus K diagram? So for this is a simple example. So the effective mass of an electron or hole can be determined by the curvature of the E over K diagram. And the way it's done is through this mathematical relationship here. E equals 1/2 mv squared equals p squared over 2m. We've been talking about that the last few slides, so that should be familiar. And for a wave, the momentum is equal to h squared times k squared. That's where this comes from. So you have the effective mass on the denominator here. So E is equal to h squared times k squared over 2m. If you take the second derivative of E with respect to k, you end up getting h squared over m. And one of the things that's kind of interesting, you have a relationship here, E is equal to h squared times k squared over 2m. You could find an equation for m just this way, right? You could say like, well, if we solve for m, then the effective mass is equal to h squared times k squared over 2e. Right? This, if we just take this equation and we solve for m, we can come up with something like this. All right. But you know, this equation could be useful in some circumstances also. But what we have in the band diagram is we just have this line here. All right, and a lot of times we don't look at the specific value of E and the specific value of K. If we can just tell from the curvature of it, then that would be even easier to deal with. So that's why instead of using this equation for m star, what they do is they take this relationship, E equals hk counted quantity squared over 2m, differentiate twice, and you get this equation. So that you take two derivatives here. And you get d squared E over dk squared is equal to h squared over 2m. And you solve that for m, and you get h squared over d squared E over dk squared. All right, so it's Planck's constant in the numerator, and then this term on the denominator. This is the second derivative of the E versus K function. So what that means is the concavity of a function. Remember how the first derivative is the slope? Second derivative is the concavity. So just by looking at the concavity of the E versus K diagram, you can it tells you something about the effective mass. So which particle here is going to have a larger effective mass? I think that's on this one. Yeah. The E versus K diagram for aluminum arsenide has 3 conduction band minima. In which band does the electron have the lowest effective mass? So think about this and think about this for a minute and then give me your answer. So what this is showing E versus K. Okay, and these are different minima of the energy band diagram. So if we go back here, you remember how like this was one of the minima of the energy band diagram. This is one minima. And it looks like there's another minima over here. This is another minima of the band diagram. So in the case of gallium arsenide, we have several minima. We have one here, we have one here, we have one here. Okay? So the minima happens in different crystal directions. This is the minima for the 100 direction. This is the minima for the 111 direction. Okay, this is a minima of a moving electron in the 100 direction. This is the actual global minima for the conduction band, and then this is the minima for an electron moving in the 111 direction. So there's different conduction band minima, and notice that they all have different curvatures. So this diagram here is just showing that. You know, you can have different energy band minima, and they can have different curvatures. So, which one has the lowest effective mass? Sorry, which one? Yeah, let's zoom in on here so we can put the letters here.
The middle one.
The middle one. Okay. Any other guesses? Middle one it is. That's right. Why is that? Okay, this has the highest curvature or concavity. So since it has the highest concavity, large concavity, large numerator here, will cause the effective mass to go down. Okay? So just by looking at the band diagram, you can tell what the electron's effective mass is. What's good, low effective mass or a high effective mass?
Oh,
Low. Why is low good?
Faster.
well.
They can move. They have higher mobility. Exactly. So, you know, when we look at a real band diagram like silicon, you know, a silicon crystal, often the electrons are, the way that silicon wafers, microprocessors are made today, they're oriented so that the electrons are traveling in the 100 direction. So this is the most commonly used conduction band minima for silicon. And you can see that it has a certain curvature associated with it. Notice that if you compare it with gallium arsenide, it has a much higher curvature. So the electrons move have a faster mobility in gallium arsenide. So if you look at an E versus K diagram, you should be able to tell me which material is a faster material, which is going to be better for high-speed electronics, for example. I just want to tie up with this last point that there's two types of effective mass, so you don't get confused. There's a density of states effective mass that's used to calculate the effective density of states in the conduction and valence bands. It is the geometric mean of the band curvature effective masses. So what does that mean? We will, in an actual practice, a material has multiple conduction band minima, and they can be in the longitudinal direction or the transverse direction, depending on which direction the electron is moving. And so if you want to find the effective mass of, considering all the bands that an electron can be in, then you have to use this a geometric mean. Just ml times mt. This is the effective mass in the longitudinal direction, and this is the effective mass in the transverse direction, and you have to take the geometric mean of those. Okay. And if you want to find the conductivity effective mass, this is the one that we'll probably actually try more often. This one, we usually just use a constant for the density of states effective mass. This one is called the harmonic mean, and we would take 1 over m in the longitudinal direction, the effective mass in the longitudinal direction, plus 2 over m times m over t, 2 divided by the transverse effective mass. And the reason why there's the number 2 here is because there's actually 2 band minima in the transverse direction, whereas there's only 1 band minima in the longitudinal direction. And so there's 3 bands, so that's why you divide by 1/3. So this is something called the harmonic mean. Okay, these types of problems, you'll be given the ML and MT that you can look up in a table. Okay, this is just a concept that I want you to know for future classes, that there's 2 different types of effective mass. All right. A lot of material, so let's just sum up then what we've covered in Module 3. So there's in solid state materials, there's hybrid orbitals that result in energy bands instead of discrete energy levels. It's okay, this has to do with the interaction of the electrons. The electrical current requires carriers and empty states. So we talked about band diagrams and what it means for a material to be conductive. If it has to have empty bands or completely full bands or partially full bands. The Fermi levels indicate which of the bands are occupied, which ones are not. So just by looking at a diagram of the bands and the Fermi level, you should be able to have an idea whether it's an insulator, a semiconductor, or a metal. We talked about density of states. So the Fermi levels and the density of states, Fermi functions, were the 2 things that allow us to calculate the concentration, the carrier concentrations of a material. The carrier concentrations also depend on the doping and the temperature. The mobility depends on the frequency of the lattice and impurity scattering, and it's dependent on the temperature and the carrier's effective mass. That's really important. You know, the mobility, it depends on how much the electron is bumping around. And there's two ways that the electron can bump around. Does anyone remember what the difference between lattice and impurity scattering was?
The thermal vibration.
Lattice is thermal vibration, that's correct.
The scan, the impurity scan when we dop like the silicon with like arsenide.
That's correct. Impurity scattering is when you dope the silicon with a dopant, and it leaves back a charged ion. So that charged ion is what causes the electron to deflect. So there's two different reasons. Which one is most significant at high temperatures and which one is most significant at low temperatures? Lattice scattering, is that significant at high or low?
High.
High, because it's due to thermal vibrations. Thermal vibrations increase at high temperature. And impurity scattering happens more at low temperatures because electrons have a lower amount of vibrations, lower energy at lower temperatures. So you can think about them as having lower momentum, so they're more impacted. They're more affected by the charges in the lattice. So we talked about that the electrons have energy and momentum, and when you change energy states, if an electron is going from the valence to the conduction band or vice versa, it has to, in some materials, in indirect semiconductors, it has to undergo a change in energy and momentum, and in direct bandgap semiconductors, it only has to change the energy, not the momentum.
So does the direct bandgap emit light because of how quickly it changes back and forth? Or is it because changing the momentum takes up part of that photon, if that makes sense? Like the energy that would be used by a photon.
So your question was, why do direct bandgap materials emit light?
Yeah, so I mean, I understand by the graphs, but is it because they're changing states so often, or what is it?
Yeah, in direct bandgap materials, the transition from conduction to valence band can happen very quickly. And it doesn't have to go through an intermediate state. With indirect bandgap semiconductors, it actually has to go through an intermediate trap state. We'll talk about that in the next module. But because of that trap state, that's one of the things that prevents that energy from being emitted as a photon. Whereas in the direct bandgap semiconductor, it doesn't have to go through an intermediate energy state. So the energy of the photon that's given off, it's very well defined by the bandgap. And that's what we want in a light emitting material. All right. Good. So I'm just going to stop this one here.